It's a piece of ulexite, also called TV stone, because it's fibrous. You see the fibers along the edge here, and it kind of guides light. So if you put an object on one side, you can see the object transmitted through. If you look on an edge, you're looking not directly down the fibers, and you don't see the image transmitted through. So with ulexite, if an image comes in this side, then it's transmitted to this side. So it's just a pipe. You form an image on one side, and it would guide the light from one side to another. So the question for today is that what a camera does? Does a camera capture light on one side and then just transmit the light somewhere else? And the answer to that question is no, that won't work for a modern camera. Let's talk about why. Computational imaging. Episode 57, Compression, Part 1. Data compression is an enormous topic, obviously could cover its own course. Here we're not interested in talking about all the details of compression and strategies for compression. Rather, we seek to understand compression as an essential part of the camera. So this is a course about camera design, and at the end of the day, the camera is a system to take optical data and compress it into digital format. Here we see one of the world's earliest computers, and this was a computer that used human labor to do calculation and was understandable by humans. But with computers, there's no expectation that they should be operable or understandable by humans, and we push to make more and more information capacity inside of computers. A camera, a modern camera, essentially is a computer that happens to have sensor resources embedded in it, but somehow we still think of the camera as something that relates to what it does for humans. Here we see a flip book, so we can make movies by flipping pages at a certain rate. Movies, images are captured at 30 frames per second. Why? Because humans can't see the motion of the page, the flicker, if we go faster than 30 frames per second. So the capture rate typically is not tied to the underlying information capacity of the optical field, but tied instead to how the image is going to be displayed for humans. The same is true with the color chart we see at the lower right, that cameras capture 3 colors because from the primary colors you can create any color that's detectable by a human, but it's not related, of course, to the underlying spectral content of the optical field. As computational imagers, we seek not to match the human capacity, but to push the limits of capture. We want to capture all of the information in the optical field, and then we can create whatever image people want on the downstream side after we have the data. So how much information is there in the optical field? Well, if we have solar illumination, we're illuminating with 1 kilowatt more or less per meter squared. That image data is then transmitted to a camera aperture. So we're going to have the image coming here. We're going to focus it through a camera aperture. The resolution is about lambda over A, as we've seen. So the angular resolution would be lambda over A. Over an aperture size of, let's say, 10 centimeters or so, that could be 10 to 100 gigapixels of resolved data. Now, in that image, we have a flux from the 1 kilowatt per meter squared that we have on the scene. The flux is typically going to be in the neighborhood of 10 to the 5th to 10 to the 7th photons per pixel per second. So we have 10 to the 5th photons per pixel per second and around 100 gigapixels. What do we do with those photons per pixel per second? Well, we can break them into time slices, right? So that if we have 10 to the 5th photons per second and we want 100 photons per time sample, we could have, let's say, 10 to the 5th frames per second, or if we want 1,000 frames per second, or if we want 1,000 photons per pixel, we could have 10,000 frames per second. But we also have color content in that data, so we might want to balance our allocation of photons between time and color. So let's say we could have 10 to the 3rd frames per second and 100 colors, that we would still have around 10 photons per resolved element that we'd have to somehow figure out how our image could be reconstructed. But between the, let's say, 10 to the 10th to 10 to the 11th pixels and our deposition into color or time, we have enough photons where we might want to try to resolve 10 to the 15th pixels per second from our 10 to the 17th or 10 to the 18th photons per second coming into the camera. So that's the quantity of data in the optical field, roughly. Now, of course, obviously the theme of this video is compression. So that data can be compressed into a smaller number of digital bits, but that's how much information is present potentially in the optical field. And here's where we get to the definition of a modern camera. That basically, the modern camera is not something that just forms an image. The purpose of a camera is to take this very large optical flux, 10 to the 15th pixels per second, and turn it into compressed data that we can handle reasonably on a computer. So we're going to go out, let's say on an optical fiber. Optical fiber, a single fiber has a capacity, at the very limit in the backbone of, let's say, 10 terabits per second. Of course, we're not likely to want to record 10 terabits per second from a camera just because of the processing capacity required to do that. Each floating point operation in a modern computer requires somewhere between 10 and 100 picojoules. And so if we're going to process our 10 to the 15th pixels per second into compressed data that could go out on a fiber, we might need to have 100 to 1,000 floating point operations per pixel, which would get us into the range of nanojoules per pixel at the very minimum coming out of the fiber. And so if we were going to have 10 to the 12th pixels per second, terapixel per second, we would have kilowatts of power. If we go to our 10 to the 15th pixels per second, we have a megawatt of power coming out of a single camera. So the limitation in the number of pixels we can record is not optics. We can make optics that will resolve gigapixel scale images, as we'll see in chapter 10. The limitation that we have is this process of compressing the data. That limits how much information that we can get out of a camera. And the very purpose of a camera is somehow to find the data from this very large optical flux and turn it into compressed data that we can mine for analysis later. By the way, the pixel count, the sort of information capacity that we're talking about here, is consistent with the data that we looked at back in episode 41, where we talked about the well capacity of optical sensors and find that a single sensor in a single exposure is going to capture between 10,000 and 100,000 photoelectrons. And if we do that, and we have enough data there that we could do that at 10 to 100 or even 1,000 frames per second and divide that into multiple colors. But this idea that we have this photon flux coming in and somehow we've got to turn that into compressed data, that's the key challenge of camera design. And our objective should be, not to match human vision, but to build machines that vastly exceed human vision, and then humans can then go and analyze in post-processing. So our initial goal today is just to talk about how does traditional compression work? What is image compression? And so we're going to talk about JPEG compression. This is the pipeline that's typical to JPEG compression. We assume we have 3-channel RGB images, and some of that has to do not with the spectral capacity of the field, but the fact that we're assuming that 3 channels is enough. And so cameras, the limitation in cameras is not how much information is in the field, it's how much information we can process. We go to 3 colors because that limits the processing requirement that we have. And then we convert the colors in JPEG compression to a chrominance space, YUV, which allows us to downsample some of the color channels. And what we find in natural images is that the luminance is required at higher resolution than the color requirement. We've already seen that we can demosaic mosaic data to recover good images, and YUV is a sampling strategy that's somewhat more sophisticated than simple bare sampling in RGB images. After we have the downsampled images by representing in a compressed color space, JPEG applies a discrete cosine transform. The reason to apply the discrete cosine transform itself on each one of the subframes or subplanes of the color space is invertible, but the reason we apply this DCT transformation is we find that we can subsample the discrete cosine transform in a way that we can't subsample in the pixel space. So we've gone into a feature space where we can downsample the data and still recover a reasonable image. We quantize that data in a way to compress its representation, and then the quantized data is encoded into a digital format that we can transmit in image format. So this process is implemented in one of our GitHub site notebooks as linked here, and we're going to talk ourselves through it in this episode and the next episode. Here we're showing a simple example of the color space transformation with a color image on the left, which is 256 by 256 pixels in RGB format. On the right, we've used OpenCV to convert it to YUV420 format. The Y channel is the Luma channel, is the upper part of the image. It's still 256 by 256. This is a weighted sum of the three RGB channels that produces the image brightness. The U, the blue projection component, is at the lower left. This is also a linear sum of the channels, emphasizing blue, and V, the red projection component, still linear sum, emphasizing red, is at the lower right. The U and V channels have been subsampled, so that now that they're 128 by 128, so the overall pixel count has been reduced to 3 times 256 times 256, to 256 by 256 image, and 128 by 128 images. So the overall pixel count's been reduced by about half. So we've already compressed the data by about half. There's some absurdity in the way this is done in actual digital cameras, because as we've seen, they can use a mosaic sampler and then demosaic, which increases the pixel count by a factor of 3, and then downsample with YUV. But that's typically ignored for ease of processing. Anyway, so given an RGB image, we've reduced its pixel count by half by this projection onto the YUV 420 format. Of course, once we have it in this compressed format, we can convert back. Here is the command for convert an OpenCV YUV 420 image back into an RGB image. And you can see along the edges of the color frames, there's a little bit of gray values that occur because of the interpolation from YUV 420 back to RGB. Of course, you could use a nonlinear projection to try to improve that, but that's what you get with the linear transformation. If we apply the same thing to a natural image, you see something like this with a piece of fabric with its original on the left. If we look at the full-scale image, it's difficult to see much difference from sampling to YUV and then returning to RGB. But as you look into details around the edges, you can see some loss of image fidelity. Okay, returning to the process of JPEG compression, we've implemented the first step, which is downsampling from RGB to YUV 420 format. The next step is to do this discrete cosine transform. So this is formally what the discrete cosine transform looks like in one dimension. So similar to a Fourier transform, but here we're using real numbers. So we'll work with cosines, basically the same as a discrete Fourier transform, but in cosine format, and it's an invertible transform. We can make a two-dimensional version of this, basically by applying the same transform in the x and the y coordinates. In image compression, this is implemented in blocks. So the discrete cosine transform is not taken over the full image. It's taken in 8 by 8 blocks of the image. And the block size is just developed from experiments with images that each 8 by 8 block in this JPEG format is independently processed. More recent compression standards may use multi-scale or larger block sizes, but this is what's in the original JPEG. So here we show one 8 by 8 block of this image, and then it's DCT on the right. And what you see, because the image is non-negative, that always the upper left corner, which is the DC component of the image, is going to be the largest component. Basically, in a two-dimensional DCT, we take each 8 by 8 block and multiply it by the weights shown here. This is a 8 by 8 set of weights, and you multiply by the weights. So in the upper left, you're multiplying the 8 by 8 block by ones, and then taking the mean of the pixel values over that 8 by 8 block. And we see at the lower right, you're multiplying by positive and negative values in a checkerboard pattern. and adding those together to get your DCT values. Because of this structure of low frequencies at the upper left and high frequencies at the lower right, you find uniformly that the low frequencies are going to dominate. So for the fabric image that we saw a second ago, here's what the DCT components of all of the blocks look like at left. And if we keep only the DC component of the image and look at, so it's a 256 by 256 image, but that gives us 32 by 32 blocks, and we're looking at the map of the DC components of the blocks, and it looks actually not dissimilar to the original image, although now it's downsampled by a factor of 1,000 in terms of number of pixels. So if we go back to the inverse DCT, so the inverse DCT is a completely invertible transformation, so it recovers the original data as you see at the left. Now at the right, what we've done is truncate, around the DCT values. And in fact, what we've done here is divide the values of the DCT by 20 and then round to an integer. This leaves just 99 integral values as compared to somewhere around 2,000 integral values in the original image. And 70% of the rounded values are 0. So 70% of the DCT has value 0, and yet you see that the inverse DCT looks quite similar to the original image. And this is the underlying concept of traditional JPEG compression, that we can quantize or reduce the dynamic range of the DCT values, and that will still tend to recover the original image. JPEG has a concept of a quantization table. So it's found that you may want to emphasize the low frequencies, which tend to contain most of the information in natural images more than high frequencies. So instead of dividing all the DCT values by a constant value, as was done on the previous slide, you divide the low frequencies by a smaller value than the high frequencies, which keeps more dynamic range in the low frequencies. And the quality factor in JPEG is a selection of the quantization table. After quantization, after you've divided by these values and rounded, you find quite not uncommonly, this is an example image on the right, and you find not uncommonly that almost all of the DCT values are 0. And so we can find a way to encode the fact that most of the values are 0 and compress our image. So here's an example from the GitHub site of the original DCT at right and the quantized block DCT at left. And then if we decompress, or if we invert this quantized DCT to recover the original image, you see that the data looks not entirely dissimilar to the original image. And so this block processing with the DCT is the core algorithm of JPEG. It's not a uniquely good algorithm. In fact, as we'll talk about next time, there are algorithms today that can greatly outperform JPEG. So when we evaluate an image compression strategy, we look at these rate distortion curves, like is shown here. These are on individual images comparing JPEG. JPEG 2000 is a later version of JPEG that uses wavelet transforms instead of the DCT transform. And then we're looking at a couple of neural algorithms above that. And you see that if the number of bits per pixel is more than 1, all these algorithms tend to behave similarly. But as we go, well below, down to, let's say, a 1/10 of a bit per pixel, there are algorithms that can still maintain reasonable structural similarity, as shown on these curves, where JPEG will tend not to. So we'll get into discussion of both the rest of the details about how JPEG works and some of these emerging compression strategies, and especially how compression strategies impacts camera design in episode 59.